we start our discussion on exponential and logarithmic functions with first defining what we mean by an exponential function. So our definition right here states that an exponential function f with a base a is denoted by the function f of x equals a. The base a is a fixed number to the x, where that fixed number a has to be greater than 0, not equal to 1, and x can be any real number here, which is interesting, but okay, we want to make sure that we understand what that means. Exponential functions are what we call transcendental functions, which seems like a kind of weird thing. What does that name have to do with anything? We have so far dealt with what are called algebraic functions. An algebraic function would be like a polynomial. In an algebraic function, we might say something like, very ick, there's a little I there. Algebraic functions would be something like p of x equals 3x to the fifth minus 2x squared plus 3x minus 17, let's say. A polynomial, right? Polynomial and rational functions are examples of algebraic function. Any number that we get from them, any number that we can get from them, are completely algebraic. Even the so-called roots, that is, the numbers that might make this polynomial equal to 0, are radicals, or some numbers that can be gotten through some sort of formula or method that's more easily found. A transcendental function, on the other hand, is a function like this one, where the function has a fixed base, like if we said 2 to the x, or if we said we could take the number pi and raise it to an exponent as well. And that base is fixed, but the exponent is not. So what kind of limitations do we have on this kind of function? Well, it turns out, for example, that we can't let the base be negative. It must be positive. It must be greater than 0. Of course, it can't be equal to 0 because 0 to the x is always equal to the 0. And it can't be equal to 1 because having a base of 1 would mean 1 to the x, and 1 to the x is equal to 1 for all real x. So we don't want that. So we base our function on the two bases like this. So, for example, let's talk about getting ourselves ready for this, and recall there are some basic rules from algebra that do govern the way that we use exponents. Some of them go like this. We have a multiplication rule that says if we have the same base and we're multiplying, we add our exponents. An example of this might be in the transcendental function. If I took 3 to the x and I multiplied that by 3 to the fourth, it would be exactly the same as saying 3 to the x plus fourth power. We simply add those exponents. If we were subtracting and I took 4 to the fifth and I divided that by 4 to the x power, as long as our base isn't 0, we're good with this. We have 4 to the 5 minus x power. But remember, our base is always greater than 0, and so we're pretty safe here. All right, a to the m to the n. If you don't remember this kind of thing, this would be as if we took 2 to the x power and we raise that to the second. Don't forget that would mean that we would multiply the exponent by 2. So this would be equivalent to saying 2 to the 2 times x power. Now, using parentheses, we do want to be careful when it comes to using parentheses, and I will make a little bit of a differentiation right here. There's a difference between saying something like this, 2 times 3 to the 2x, let's use that, versus saying something like 2 times 3 to the 2x. In the first case, only 3 is raised to the power 2x. We multiply that result by 2, that's it. In the second case, we would be able to multiply those two bases together and say that's equivalent to saying 6 to the 2x. Of course, by this rule, we could also rewrite this as 2 to the 2x times 3 to the 2x. So that even though the bases don't match like it did over here with our multiplication rule, we could still distribute an exponent over multiplication. Now, only over multiplication, so do be careful with that. One more quick note here. Anytime we raise a base to the power 0, we get 1. 7 to the 0 would be 1. And anytime we have a negative exponent, that negative exponent changes the position of the base. So a to the negative n would be 1 over a to the n. In a real quick example, if I told you I wanted to simplify something like 3 times 5 to the negative x, what goes to the denominator? Exactly, only the 5 to the x. That becomes 3 over 5 to the x, because by our rule, the exponent only applies to the very last thing which it's attached unless there's a parentheses. Go back to rule 4. So this should set us up in a good position to handle the rest of our work.